transmitted. So thank you very much. So this is what I'm going to discuss in the part that involves, it's more or less introductory, but the part that involves me, it involves the chairperson, Laura Foini, and Silvia Papalardi. So Eigenstate thermalization. So the questions we will ask are about quantum systems that are going to be chaotic, and meaning that we will assume that there is not a large number of conserved quantities, and the things that happen as soon as we begin to ask questions about single eigenstates, and the kind of thing that emerges. So, oh, sorry, not that. Which one is it? Okay, good. So imagine you have a generic Hamiltonian, generic meaning reasonable, short-ranged, and without too many constants of motion. And you also have a reasonable observable. So again, something that is well-defined, local, etc. And we will assume that the number of degrees of freedom is large. So this is the main point here. You have a spectrum of the Hamiltonian, and then you have the level spacing, which is the smallest energy scale, which is extremely small, but extremely means ridiculously extremely small. It's a quantity that is unbelievably small. It's an exponential of the number. And then you have the energy densities, the scale of energies divided by the number, which is a gigantically bigger number, which involves a huge number of levels. Now, as a physicist, normally you would be interested in things that are related to energy densities or at most to energies, but this kind of scale, you would perhaps think that you are not so interested. But then sometimes one does work with single wave functions. So we have this kind of dual situation. And now, oh, sorry. And now I just put the spectrum vertically, and then imagine that I perturb my Hamiltonian with an extremely small perturbation. By extremely small, I mean compared to the energy, it is ridiculously small, so small that you won't expect any of the physics to change at all. And the quantity you have to look, if you want to see how big is a perturbation on an energy eigenstate, is this quantity, and this is the level spacing, and you see that this quantity very soon becomes gigantic. So when you are looking at single eigenstates, any perturbation which is grotesquely small is enormous for the eigenstates. This is the main message. So when you're asking questions about the eigenstates, you're asking extremely bizarre questions because they depend on everything. Okay, but you still want to ask such questions. Which one is it? I try all of them. This one, this one. None of them works. No. Okay, it works with you. I will call you again. Okay, so imagine now there is, as I said, very much comfort here between this scale and the reasonable scale. So let us place ourselves in a very comfortable range of energy levels, which is enormous or big with respect to the level spacing, but very tiny with respect to the energies. This is a scale that is, again, sensitive to everything, but doesn't impact the physics very much. Okay, and this is the world of randomness that we have to discover. Why of randomness? Because we just said that these levels themselves and their statistics within them is extremely sensitive to everything. And to an extent that whatever happens to them can change them dramatically without impacting directly the physics, except for, of course, single wave functions. This is the world we are interested in. Oh, good. So now let us look at a matrix element of an operator A, which is also local. So for example, this is a spin chain and you're looking for, I don't know, the magnetization. So what you see, perhaps you can see, is what the matrix looks like. And this is very generic. If your operator is reasonable, if your Hamiltonian is reasonably local, what you get is that your system, your matrix elements are very much distributed around the diagonal, which means that here there's almost nothing. The elements are almost zero. There is a drop here. But remember that the scale delta, the one that we said, let's say 2000 levels, is tiny, tiny, tiny with respect to energies. And there are plenty of matrix elements here. So we have this bizarre situation that we have these matrix elements here that are, in a sense, sensitive to everything, but at the same time, they are distributed relatively close to the diagonal and not outside. So this is already pointing in the direction that we will have to do a statistical or semi-statistical treatment, but it won't be a simple random matrix one, because if I do a true random matrix, I destroy everything, and I need this structure. Okay, so this observation was done by lots of people. No. Yes. Oh, shh. Sorry, I'm. Okay. I guess this is the next. I'm not sure, but experience is. Okay, yes. So the first step was done by people like Berry, Deutsch, and Srebnicki in the 80s, 70s, 80s, 90s, was to realize that, first of all, let's think of the diagonal of this matrix, A. So what they realized is that, I'm not going to too much talk about this, but this is the simplest of all observations. The wave functions are, in some sense, if you can represent them in phase space, are sitting more or less on an energy shell. So you would expect that the expectation values of the operator A should vary smoothly with this energy scale. And so they assumed that basically these elements, AII, are a smooth function of the energy density plus small fluctuations. And this gave the field the name eigenvector thermalization, eigenstate thermalization hypothesis. It's a very bizarre name. It means that a single eigenvector, eigenstate, in some sense itself probes the entire energy surface. So eigenstate thermalization doesn't mean thermalization between eigenstates. It means thermalizations of a single eigenstate, and it was supposed to be a kind of oxymoron said on purpose. Okay, so this was the first step. I'm not going to insist too much on this one because this one is the easy one. Now, let's go back to philosophy. We said that the matrices are extremely sensitive. The eigenvectors, the eigenstates of the Hamiltonian are extremely sensitive to everything. So extremely sensitive to everything means if I perturb a little bit, the kind of thing I see should not change dramatically. So what we are going to take as our guiding principle is the following, and this is the crucial point in all my talk. You have your matrix in the basis of some Hamiltonian, and then a meteorite passes near Jupiter and already perturbs the system very much if you look at the nearby eigenstates, and so that the basis changes a little bit, but it changes a little bit between relatively nearby levels. So we will assume that anything can do a perturbation of this kind. Look at this matrix. This is a matrix which is mostly empty, and it has little unitary blocks, independent unitary blocks along the diagonal and in the famous scale delta. So it's a local reshuffling of levels. Instead of doing all the perturbations and averaging over possible weak perturbations, we will do this as our proxy. Our proxy will consist on assuming that whatever we get, it has to be invariant with respect to such transformations. This is the main point of this talk. If these were a full unitary matrix, you would be doing random matrix theory, but you cannot do that because you know that you want to get something close to zero away from the diagonal. So that structure you cannot destroy. You can only randomize within this famous scale, which is intermediate between level spacing and the densities. So, okay, what do you conclude? Okay, very easy. Take one element, Aij, which is here, and apply one of these random transformations. It's you are transforming with these two little blocks because I and j are away from the diagonal. And you can see already that if I let u, which is a rotation, be anything, and I let v, which is a rotation, be anything else, this thing, if it was something non-zero, by turning, its sign is going to oscillate like mad. Because you can, even in this case, make it easier and say that this is a change of phase, for example, which is a particular case. So if I postulate, suppose you come to me and you say, I expect this to have an average. I would say no, because just any perturbation will kill that average. Because this essentially is a randomizer for this element. Okay, so the average we should expect these elements outside the diagonal or somewhere, anywhere outside the diagonal to have is zero with this argument. But let us see who can resist this operation. Well, try this one and apply this transformation. And then you discover that no, that thing in fact resists. Why? Because it's a modulus, first of all, so it has to be positive, and any rotation, local or not, will keep it positive. But also the transformations are done in such a way that you can see just by averaging over the group of rotations, these are the tiny little rotations around the diagonal, that this is a thing that you expect has to have an average. So in this way, you construct yourself a kind of ensemble, but you don't do it with big unitary operators as you do if you do random matrices. You do it with these semi-local rotations to guess who can be good. Okay, so now that we discover who can have an average, we will postulate, as Srednicki did 30 years ago, that, okay, this square that I think you can see, Aij squared, on average means locally around a certain I and j, will be some function of omega is the difference of energies, and E is the sum. There was this in a previous transparency. So we are going to change these coordinates from I and j to the plus is the sum, omega is the difference from now onwards, okay? And he postulated, okay, this is going to be, let's say, a smooth function, so that the average, you remember this degradé in blue that you saw away from the diagonal, on average is given, if you take the square average, by a smooth function. But their magnitude, how big is it? How does this scale with the size? So if I take a typical element, it will be distributed like this, but there will be a global scale. And this Srednicki asked himself, and he did probably the following calculation. Okay, he did a calculation of something physical, and he said, okay, I'm going to impose that things are physical. So, okay, we will do this in a minute. But before that, I need to do a little intermezzo, because the thing that is physical that he calculated, or he should have calculated, is something that I need to explain a little bit to you, 2 slides. So you know that when you do quantum, you calculate commutators or anti-commutators of your operator. A of t is the evolved operator, you have it here, with the Gibbs measure, and then you normalize. This is what you need. Now, it turns out that there is a much cleverer quantity, much better behaved quantity from which you can get these, but it's much nicer to work, and it's this one. So it's the same thing, but with a measure split in 2. It has better analytical properties, and what you have to know is if you do a small calculation, if you evaluate it in this complex time, you get back this one. So take it as a change of plans. Instead of calculating the usual things, take it on my word that this quantity is a nicer one, but it's a physical quantity, okay? And just to defend it a little bit more, the split quantity, as you see here, this is for Q things, is the one I am defending. All these split quantities that have, instead of having the Gibbs measure here, they have it cut into slices, has the beautiful property that if you want to write the KMS conditions for those who are specialists, that is to say the fluctuation dissipation theorem that is so important, instead of taking a nasty form, which it usually does, it takes this beautiful, simple form. You just reverse the times and conjugate, and this is the equilibrium condition. So if you want to take home messages, these split measures, believe me, have much better analytical properties, are equivalent, or you can transform them into the usual ones, so there is no loss, and everything is encoded in a super simple way. Okay, so let's go back to our story of Srednicki. So he wanted to calculate this quantity here, and if you put everything inside in the definition, you have to calculate this. This is the F. Okay, so now we're going to plug in the form that he had gotten to. Remember, he said a smooth function of the energy difference times something that should scale somehow with the size. And let me try to see and guess. This was our object. Okay, so let us put this inside, put it here. We have this thing that has to scale with size. And the only thing to realize is that when you go from sums to integrals, because you have a certain density of level, you have an entropy that appears for each integral. No, because instead of summing over many levels, you're integrating. So for every delta E, you're catching an extra entropy factor. So if you understood this, you understood everything. You have these 2, because there are 2 integrals here. In the normalization, there is only 1. And you discover that the scaling with size times this factor has to be equal to this factor to get something that is decently normalized. In conclusion, what you need is to accept the fact that each matrix element has this smooth distribution multiplied by e to the minus entropy. So they are really tiny, the matrix elements, but they contribute to this quantity, which is important. So they are there. They are much, 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 much smaller than the diagonal, but there are many, many because you're adding over them. And so, and they have to be, if you want your quantities to be decent, of the order of e to the minus s. Otherwise, things don't work. So this is what Srednicki realized. By the way, he realized because he was teaching a course and he thought that everybody knew this, but it seems that it wasn't the case. Where are we? So, I don't know, it turns. So, okay. So if you put inside, there was, remember, a 2s, and there is you accepted that scaling, and you end up with this beautiful formula, which tells you that this function, which is the one that decides the shade of blue that I drew in the matrix element, so how big they are, is nothing but the Fourier transform in time of the function f I defined. So now we have everything we need, and we can write the eigenvector thermalization hypothesis in its version like that. And then the one you will find in the books is written rather, instead of talking about averages, is written this way. So a smooth function of the energy density in the diagonal plus, this is just a random number plus minus 1. This is this function that is smooth, that tells you the shades of blue in the matrix element I drew at the beginning. And this tells you, it's a square root, it tells you the typical amplitude, which is simply the square root of the entropy. So sorry, it's a square root of the density of states divided. So it's a tiny number. So once you condensate everything like this, this is the one you will find in the books. And this was the situation roughly until 3 years ago. So, and it's perfectly okay. And then you say, well, and these numbers are going to be, let us assume, independent. But remember that we didn't say anything about independence of diagonal elements. They are kind of random, but are they really independent? Well, the answer is yes and no. So this is what you will find in books, and mainly what you will find, for example, in the lovely review of Rigol, Kafri, and Polkovnikov. But then something happened. Okay, so let me recap what we said. There is a typicality argument that it's as a basis of everything. We're saying we have a matrix, we have an operator which we're writing in a basis, and we are saying that small rotations, reshufflings that are local or relatively local in energy don't do anything dramatic. So you expect your distributions to be stable with respect to that. And then you just adjust the quantities so that the observables have reasonably normalized forms, and that's all. Okay, that's okay. But then something happened, which is the following. The people in string theory, Maldacena, Schenker, and Stanford, they were interested for reasons that are out of this talk, of calculating this quantity. What you can say about this quantity, look at it, it's the split measure, but it has times 0t, 0t. There is only one thing you have to know here about this quantity, is that if you plot it, this behavior around here, the way it drops, defines the Lyapunov exponent. So it's a measure of the chaos you have. Lyapunov exponent is how two trajectories diverge. This is the quantum chaos definition that they were looking for, because black holes have to be very chaotic for other reasons. And so they were computing that. And at the end of the day, they decided that this was the best quantity, you plot it, you look at it at certain times, and from there you can read the quantity you want. Okay, and then you get a Lyapunov exponent, that looks good. And now you say, oh, okay, but Lyapunov exponent means the system is chaotic. On the other hand, I know what the system does when it is chaotic. It does the Eigenstate thermalization hypothesis. We just obtained it a minute ago. So it's very clear what we have to do. Well, this is going to be a long operation if I want to go one back, but I take the ansatz of ETH, I put it inside, take the sums over all intermediate matrix elements, and I'm done. So that sounded great, except that, okay, so the program is take this form, which we wrote a while ago, plug it into the other form. Remember that it came from here, this form. Plug it into the one with 4. It's also called the OTOC, out of time order correlator. And I have my OTOC for a chaotic system. Great. But then you begin to be worried because you say, okay, but wait, my ansatz this way was obtained from, or can be obtained from computing this quantity, which is a 2-point quantity. And now I'm plugging it in to calculate a 4-point quantity. So all the information, if I'm right, if what I'm doing is right, is already here. So why am I doing the 4-point quantity at all? Is it possible that the 4-point quantity is not needed? Okay, let's see if it's possible. So let us go back. It is not possible. And this example is well known for ages. This is work, there's a beautiful paper by Posch and Delago for classical, but nothing changes here. Take hard disks and take the diffusion time that takes for one particle to move around. These particles are rattling, they have a certain energy, okay? And take the Lyapunov time. Okay, so the diffusion time, you know, is a 2-point correlation function. The Lyapunov time, they are telling us it's a 4-point correlation function. So we want to know if it's true that one can get one from the other. So is it true that I can get a 4-point function from a 2-point function this way? Sounds mad, but I'm just proving that it is mad. So if the particles are widely spaced, the diffusion is fast, and the Lyapunov is relatively modest. It exists because there are impacts and trajectories do diverge, but you get a decently small Lyapunov. So this quotient is small. Now consider this very tightly packed system. Now the diffusion is really complicated because this guy, it's a glass. This guy is rattling against its neighbors, but before it gets the opportunity to move around, it'll take it a long time. So the diffusion is extremely low. But the Lyapunov is gigantic. Why? Because the rattling here, for each time you rattle, these are two concave surfaces. So trajectories, if you think in the space of trajectories, are diverging like mad in each collision, and they are super frequent. You're catching more Lyapunov. So, okay, with this, I hope I have convinced you that trying to get the Lyapunov from a 2-point function is utter madness, okay? Okay, is everybody convinced about this fact? Okay, so now we go back to our problem and we conclude that we cannot plug the ETH ansatz in here. So now let us put inside the matrix elements, this and this are the same thing, and we want to know the average of this. But now we say, wait, there are correlations here that were neglected, surely, in the usual ETH ansatz. Otherwise, I'm not going to get a different result. And otherwise, I'm going to be forced to conclude that the 2-point function has all the information, which is, as I showed you, madness. Okay, so now let us consider one simple one. All indices are different. So the usual ETH you will find in books and reviews tells you that this is 0 because there is no repetition. There are no two A's that are the same. If they are independent and the indices are all different, this has to be 0. But we want it not to be 0. Let us see if this is possible. So we go back to our old philosophical trick, and we apply these matrices, which are almost diagonal. Here there are all the indices I, J, K, L. And we turn these things around with this, and we see who can resist and who cannot resist. Who is going to have an average that is 0 and who is not. And indeed, you discover that the guys that survive this operation, such that this operation doesn't scramble down to 0 the average, you can write them in diagrams. A diagram is just a matrix elements, and each point is an index. So Aij, Ajk, Akl, Ali, all different. Or AIL, ALI, AIJ, AJI. Notice that here there is a repetition of I 4 times. This is why it's this diagram. So this classifies the terms. And you have this one, Aij to the 4. And we find that all of these can survive. But this one is small. Why is it small? Because it has too many of these A's and too few indices. So in the sums that you will do, it won't contribute. But this one will, and this one will. And now we have a mess, because instead of having the beautiful ETH of the past, we are driven to this world of many possibilities that are non-zero, that gives you all the possible correlations that up to now had been neglected. And we know that they have to be there, because we know that when we want to calculate 4-point functions and such, they have to contribute. So what do we do next? And now we are entering the last part. So this was an observation that we did with Laura, and then from here onwards, this is work we are doing with what we have done with Laura and Silvia Papalardi. So if you look at these rotations we were doing and try to estimate, look at this one, Aij, Aji, AIL, LALI. It's a very special thing that corresponds to that diagram. You discover that you can cut it in two. It's not hard. Just by applying these rotations and so on, it's a kind of central limit theorem like situation. You can always cut a diagram like so. It's not a hard argument, and you do it with this typicality arguments. Sorry, I haven't mentioned it. This argument of saying my properties have to be invariant with respect to some group of rotations is a long story, starting at least from von Neumann, and it's called typicality, and it has followed a different route. It's not the same route that Srednicki took, although ideologically is extremely close, but I'm not aware that Srednicki had read this part of. Okay, this one, as I told you, has too many repetitions. The one you see there, the melon. Now, these days you call that a melon diagram, sorry. It's a vanishing melon. Okay, let's say it's gone. It was vanishing in any case. Now, this one contributes and has no repetitions. So this one was neglected before. We have to accept it now. Okay. And now we have the three, those that we can cut, those that we can throw away, and the glorious one, the one without any repetitions. And now we have to, yes. And now we have to consider these. Okay. So we can calculate it with exactly the same thing we did for the 2-point function. We calculate the OTOC, the thing with the 4 things. You put all the entropic factors and you ask that the result be of reasonable order. And you conclude that this correlation exists is related to a time correlation function, but now with 4 times, and is tiny. Remember that the other correlation was e to the minus s. This one is e to the minus 3s. So you're going to ask, well, why don't you throw it away? It's a correlation that is extremely small with respect to everything else. Well, no, it is extremely small, but it has too many indices, meaning that when you're going to do sums, you're going to sum them many times. So one thing compensates exactly the other, and the conclusion is don't throw it away. Okay, and the argument is completely identical. Very good. Now we discover that everything we need to calculate are sums of products, of matrices, matrix elements. This is Aij, Ajk, AKL, LN, and so on, which have this cactus form. These are the ones that dominate. Very good, but we know more. We know that we can sever the leaves of the cactus. And in fact, just as we did before, the cactus is just the product of its leaves. And the leaves are all of this beautiful kind where there is no repetition at all. Okay. And now we discover that the beautiful beautiful world of ETH of 3 years ago has proliferated into innumerable correlations, but those that come from the cactuses with severed leaves, so actually the leaves of the cactuses. And now we discover that this random world, the world at the scale that is many levels, but not so many that you get a big energy difference, is dominated by this algebra, or if you want, this ensemble of matrix theories, and which is much more complex than ordinary matrix models, but which you can think in many aspects in the same way. And you know now that all correlations that matter at this level are leaves of cactuses. So this is everything that matters. When you are given an expectation like this, you cut it according to the repetitions. So if an index is repeated here, I sever it here. That's what we did before. And you just have to calculate these leaves. And now, once you've done this, you discover that what you have discovered is that you have rediscovered the free cumulant expansion, the so-called free cumulant expansion. So you all know the cumulant expansion. You're given definitions of connected correlation functions. The definitions are entirely arbitrary. They are given in terms of the usual ones. What is good about them? That the Gaussian kills them as 0. That's the ordinary cumulants. It's just a linear transformation of correlations done in such a way that for Gaussians, all the ones above the second one are 0. Now, clever mathematicians invented something similar for matrices, and they discovered the free cumulant expansion, which is a non-abelian, if you want, variant of the cumulant expansion. And we have discovered that we have fallen into their laps, because what we are doing here, discovered on the basis of typicality, is exactly each one of these guys is a free cumulant. So this is the only thing you have to calculate. Just like normally when you calculate cumulants or correlation functions, you only calculate the connected ones. The other ones are obtained as a result, but all the physics is in the connected ones. So we get to the end. We have discovered that the eigenstate thermalization hypothesis, which used to be very simple, is no longer simple, unfortunately. But if you want to do it correctly, you have to take all these things into account. But there is an interesting thing, is that now you can restate the eigenstate thermalization hypothesis just by saying that the free cumulants of this average, which are defined in Wikipedia, you can calculate them as the product of different indices. And this is where ETH enters. If the system is integrable, where none of this is valid, you can still define free cumulants, but you cannot obtain them as sum over different indices. So this is ETH for you now. Okay, thank you very much.
Thank you very much, Jorge, for this night's talk. Are there any questions? Yes.
Thank you for this nice talk, Jorge. I was wondering whether this decorrelation assumption that you make for the repeated I configurations, whether you can control that and whether this is subdominant also in your family of cactuses. So that's
Yes, control. I think that within this, here's where these rotations, micro rotations, assumption, because now it's an assumption, but still. So you say the average over these micro rotations corresponds to cutting. That's a control you can have. Control, real control in the sense of a real single system. Can I prove it? No. So it's sort of, it involves the assumption of robustness with respect to local in energy rotations.
Sorry.
Thank you, very nice talk. So I have a question. So as far as if I understood correctly your statement, now you have all this infinite contribution, which would be describing the off-diagonal elements. But I mean, I don't understand. So the ETH, as it was known until 3 years ago, as you said, I think that can be, so the correction to the off-diagonal elements can be shown to be more or less correct numerically. So how does this compare with that now?
So you are asking if I can say that the corrections are small with respect to what ETH was. Sorry, there's a lot of echo.
Yeah, no. So I mean, as far as I understood, these corrections are all of the same order, so you should keep them into account. But I mean, I thought that numerically the correction which were known before were kind of shown to be correct. So now I don't know how this compares.
The corrections to what? Sorry.
I mean, the off-diagonal elements, how they decay exponentially. So I mean, now can you show that instead those were not correct and these are the new correct ones?
The thing is that if you take and you do the statistics of the matrix elements of the diagonal, let me say another thing. Suppose you were saying off-diagonal elements are very small and diagonal elements are very large. That is obviously true. The diagonal elements are enormous and the off-diagonal are very small. That's true. But why do you keep them? Well, you keep them because you know that in sums, they appear with so many indices that they will contribute. Here is the same. When you look at and you want to test ETH, you don't see any contradiction of any kind because the correlations between the elements are tiny. And so every test that was done was okay in that sense because the correlations scale like much smaller. Just like out of diagonal was tiny with respect to diagonal, 3-point correlations are tiny with respect to 2. But it comes into big sums. Yeah, so with Laura, we did a test. It wasn't high-tech numerical, but it was a test with 4 different indices. And that should be 0 in ETH, and you can tell clearly that they are not 0. So you take IJKL different, multiply the diff of the cactus, Aij, and that should be 0 if the ordinary ETH would be true. But it is not.
Okay, I suggest that we keep the discussion for later and we move to the next talk. Thank you again, Jorge.